welcome back to my channel. Today we're going to be talking about Demorph's theorem, and this is of course continuing with complex numbers. So please go ahead and watch my previous numbers on complex number. Now the Demorph theorem was created by Abraham Demorph, and the story behind his life is actually pretty interesting. So you can go ahead and do further research on him. Now let us start out with the rectangular form of the complex number. We know it to be z equal x plus iy. Good. Now, what if I want to raise this complex number to a power? I would have, let's call it power n. I would have z to the n is equal to x plus iy raised to the n power. Now, of course, we can go ahead and expand that. But when n becomes very large, then of course the expansion of x plus iy to the n becomes a bit difficult. Even using binomial expansion. But what if we were to take this complex number and we were to express it in its polar form? Now, z as we have it in its polar form would be equal to r, which is the modulus, into cos theta. Bear in mind that theta represents the argument, plus I sine theta. Good. Now, if you want to raise this complex number to a power, we're going to have to raise the entire bracket to that power, including the r that is on the outside. But what we want to investigate is what happens when I raise the polar form to different powers. So I'm going to start by using a power of 2. So we're going to say let n equal 2. Now if n equal 2, this would imply that z squared equal, and note here now I'm going to use a box bracket so we can capture everything, r open bracket cos theta plus I sine theta. Alright, put my bracket here. I'm going to have my box bracket to the second power. So this implies that z squared equal, by laws of indices, if you have a product and you raise it to a power, then each term would be raised to that power. So we have r times the entire bracket. So r would be raised to the second power, and the entire bracket would also be raised to the second power as well. So I would end up with r squared open bracket cos theta plus I sine theta raised to the second power. Good. Now, we're compatible with r squared. We can see clearly what is going to happen there. What I want to find out is what will happen with the cos theta plus I sine theta. So I'm going to be taking out that part. So I'm write a statement here that says taking, and probably we could change the color, cos theta plus I sine theta all raised to the second power. What is going to happen there? Alright, let me go back to black. So here, it means that I'm going to have to multiply that by itself. Now, cos theta plus I sine theta is a perfect square. So we can use the shortcut. So we're going to square the first term, which is cos theta. Now, when I square cos theta, I'm going to have cos theta all squared, which we can shorten and write as cos squared theta. To get the middle term, we'll multiply the first term by the second term by 2. So I'm going to have plus I 2 cos theta sine theta. And to get the last term, I'm going to have to square the I sine theta. Now, of course, I squared is -1, so I'm going to have a minus. And sine theta squared, we can simply write it as sine squared theta. Now, what we want to do next is to group, because once you expand a complex number, you want the real parts and you want the imaginary parts by themselves. So I'm going to have cos squared theta minus sine squared theta. And of course, this is my real part, plus I 2 sine theta cos theta. Now this brings me to something very important. I'm going to change the color here. What I'm looking at here are what we call double angle formulas. So we can say recall. Two things we can recall here. Let me put them in red. That cos 2 theta, which has several manipulations for this identity. But the one we're interested in here is the cos squared theta minus the sine squared theta. And also that sine 2 theta is actually equivalent to 2 sine theta cos theta. So what does that mean about my identity? What it means is that my identity is now going to become cos 2 theta plus I sine 2 theta. Now bear in mind that we had taken out the bracket part, which is a cos theta plus the I sine theta square. So now I need to recombine everything. So I'm going to recombine, right? So this implies that z squared equal, I'm going to have r squared, open bracket, cos 2 theta plus I sine 2 theta. So realize that we start seeing a pattern here. We had z to the second power. Notice r becomes squared. And notice that the 2 goes in front of the theta for cos and sine. But we can't just make a deduction here. We're going to be looking at z cube to further continue this expansion. But we'll give you a second to just look at it and see how the identities are building up very lovely in this particular complex number here. So from our investigation using z, we found out that z squared is equal to r squared into cos 2 theta plus I sine 2 theta. What I now want to investigate is what happens with z cube. So technically speaking, I want to find out what z cube is. Let me go here. Z cube would basically imply r open bracket cos theta plus I sine theta, all of this being raised to the third power. But now we're going to apply some laws of indices, because we can say that z cube is actually equal to z squared times z, right? We already know what z squared is. So this would imply r squared into cos 2 theta plus I sine 2 theta. All of this multiplied by z, which is r into cos theta plus I sine theta. Now, let us see where the expansion here takes us. Because we're multiplying here, we can take the product r squared times r, which would give us r cubed. Now I'm going to open my big bracket because I'm going to have to expand this. So we have cos 2 theta times cos theta. So I'm going to have cos 2 theta, cos theta. Then I'm going to have to go cos 2 theta times I sine theta. So I'm going to have plus I cos 2 theta sine theta. The I sine 2 theta will now multiply each thing. So I'm going to have plus I sine 2 theta cos theta. And then we have, let me see if we can minimize this to get some more space. So we're going to have I sine 2 theta times I sine theta. I times I is minus 1. So I'm going to have minus sine 2 theta sine theta. Good. Now, the next step is always to do our grouping. So this becomes r cubed into, I'm looking for the real parts here. So I'm going to have cos 2 theta cos theta minus sine 2 theta sine theta plus I, taking out the imaginary part now, I'm going to end up with cos 2 theta sine theta. So this is going to be cos 2 theta sine theta plus sine 2 theta cos theta. All right, close the bracket there. Now, what can I get out of this? What I'm seeing here is compound angle formulas. And the compound angle formula, so let me just say here, recall that what? Cos of A plus B is equal to cosine A cosine B minus sine A sine B. And if we have the sine of A plus B, this is going to be sine A cosine B plus sine B cosine A. How is this applicable? When I look at cos 2 theta, cos theta minus sine 2 theta sine theta, my A appears to be 2 theta and my B appears to be theta. So technically speaking, this identity becomes r cubed, open bracket. What I'm going to have is cos of 2 theta plus theta plus I sine, open bracket. If you look at the identity there, that's the compound identity or the compound angle formula for sine. where you have cos 2 theta sine theta. So it becomes the sine of 2 theta plus theta. Let me close the bracket there. This breaks down to give me r cubed into cos 3 theta plus I sine 3 theta. Now, let us look at a few things here. Bear in mind that this is z cubed. So let me just put that in here. So this is z cubed equal. Z square was, the first thing we have on the screen, r square into cos 2 theta plus I sine 2 theta. Now look at z cubed. It is r cubed into cos 3 theta plus I sine 3 theta. It's almost as if we can actually make a deduction here. What if we wanted z4? We probably could guess z4. Let me change the color to red. So here I would be thinking that z to the fourth power would be r to the 4 into cos 4 theta plus I sine 4 theta. That's a deduction that we can make. Deduction. But to validate this, we're going to look towards mathematical induction, because we have done it for z square, we have done it for z cubed. We could prove it for z to the 4, but just to validate all powers of n, we're going to take on mathematical induction. Alright, now since we can't construct a proof for every possible value of n, we're going to use mathematical induction to generate a general proof and to see if this is true for all possible values of n. Alright, now we had proven initially for n equal 2 and n equal 3. Good, so in my first step of induction, I could just recall what had happened when n equal 2. So proof for n equal 2. Now when n was equal to 2, we would have had r into cos theta plus I sine theta raised to the second power, which we found out to be equivalent to r square into cos 2 theta plus I sine 2 theta. Good. Now once we have gotten that out of the way, we can now generate our assumption. So we assume true for n equal k. So what am I assuming? I am assuming that if I have r into cos theta plus I sine theta, and all this is raised to the k power, then what I'm going to end up with is r to the k into cos k theta plus I sine k theta. Good. Now that we have our assumption, we want to prove for n equal k plus 1. So prove for n equal k plus 1. Now what do we do here? So what we're trying to prove is for r into cos theta plus I sine theta, all this being raised to the k plus 1. This is where some laws and indices come in now. If I have all this raised to the k plus 1, by laws and indices, this can be written as r into cos theta plus I sine theta, all this raised to the k times r into cos theta plus I sine theta. Now let us recall a few things. In my assumption step, we had assumed that r into cos theta plus I sine theta all to the k would have been equal to r to the k cos k theta plus I sine k theta. So all this is now going to multiply r into cos theta plus I sine theta. Good. Now by laws of indices, r to the k times r to the 1, by laws of indices we add the power, so we're going to have r raised to the k plus 1. Now, where the brackets are concerned, that is what I'm going to have to expand the long way. So when we have cos k theta times cos theta, I'm going to have cos k theta cos theta. Then we have cos k theta times I sine theta, so we're going to have plus I cos k theta sine theta. Then we're going to have the I sine k theta times cos theta, so I'm going to have plus I sine k theta cos theta. And then I'm going to have the I sine k theta times the I sine theta. And we know that I squared is -1, so this becomes a minus. So minus here So that's minus sine k theta sine theta. Good. So here we see the compound angle formulas coming out again. Let me remind you what they are. It says that if you have cos of A plus B, we're going to end up, and we did this initially also, so you'll actually recognize it. You're going to have cos A, cos B, minus sine A, sine B. And if you have the sine of A plus B, what you're going to end up with is sine A cosine B plus sine B cosine A. So how does this apply to what we have here? What you're going to end up with is r to the k plus 1, open bracket. I'm going to have cos, open bracket, k theta plus theta plus I sine k theta plus theta. Good. Which breaks down to r to the k plus 1 into, alright, cos, so we can say k plus 1 theta plus I sine k plus 1 theta. And this is exactly what we wanted. So for any value of n, the Morph theorem holds true. Very powerful theorem that we have here. It does hold true. Alright, so while we had proven it for n equal to and n equal 3, we can't prove it for all possible values of n, so we had to generalize it. And in generalizing it, we decided to use a mathematical induction. And as it turns out that for any value of n, this theorem actually holds true. Now here's a simple example. Simplify z to the 8 if z is equal to 1 plus I. So the first thing I want to do with z is to put it in its polar form. Now in the polar form, we know, well, let us recall what the polar form says. It says that z is equal to r into cos theta plus I sine theta, where r is a modulus and theta is a principal argument. So let's just go with the modulus. Now the modulus of z would be the square root of the real part squared, so that's 1 squared plus the imaginary part, which is also 1 squared. This turns out to be root 2. Now to get the principal argument, because the imaginary part and the real part is positive, we know it's in the first quadrant, we don't necessarily need a diagram, but just for reinforcement, right, it's going to be in the first quadrant. So the argument of z, which is the same thing as saying theta, right, which is equal to theta is equal to tan inverse of the real part, the tan inverse of the imaginary part, which is 1, over the real part, which is also 1. This turns out to be pi over 4. So we can now express z in its polar form. So z is actually going to be equal to r, which is root 2, into cos of pi over 4 plus I sine pi over 4. But what do I really want? I really want z to the 8, which would really be based on my complex number, based on the Morph theorem. Let me go first with root 2 into cos pi over 4 plus I sine pi over 4. And all this would be raised to the 8th power. Now based on the Morph's theorem, it says that if we have z to the n, it's going to be equal to r to the n into cos n theta plus I sine n theta. So this means that z to the 8 is going to be equal to root 2 to the 8, open bracket. I'm going to have the cosine of 8 times pi over 4 plus I sine 8 times pi over 4, which breaks down to root 2 to the 8. So this is 16 into cos. We have 8 times pi over 4, and 4 into 8 is 2, so it's cos 2 pi plus I sine 2 pi. So really I need to just evaluate the cos of 2 pi, and the sine of 2 pi. So this is going to be 16 into 1 plus I, and the sine of 2 pi is 0. Alright, so that's gone. So all we have is 16 times 1, which is equal to 16. And this is actually pretty interesting, because what this is saying is that if we take the complex number 1 plus I and we raise it to the power of 8, what you're going to end up with is a real number. Not a complex number now, but a real number. And that real number is going to be 16. Pretty interesting here. So we end up with a real number as our result.